Okay, it's 8 a.m. California time. Good morning, California. Good morning, North America. And good afternoon to our friends in Europe. And good evening to tinyML enthusiasts and experts in Asia. Welcome to the tinyML Talks series. Today, we are very excited to have Dr. Martino Sorbaro from SynSense, and he's going to give us a presentation on a very interesting topic, which is spiking convolutional networks for visual classification below 1 millimeter. I think that's the first time we're talking about spiking computing at this series, and it's going to be very interesting. So please ask your questions as we go. Before we start, I would like to acknowledge our sponsors, tinyML Talk sponsors, without whom this series would not have been possible. ARM, DeepLight, Edge Impulse, Maxim Integrated, Kixo, Reality AI, and SynSense, the company where Martina works. If you're interested to become a sponsor and support this series, please contact Betty at tinyml.org for more information. I have even more exciting announcement here. So we are very happy to announce that we are going to have our third tinyML Summit 2021 coming in about 8 weeks. It's going to be in March, in the end of March. So the program is posted on the website. You see the link there, tinyml.org/summit. And I just want to make a couple of highlights there. So in a nutshell, the summit is going to be a premier quality event. It's going to be very interactive. What is important, we are going to have it live. And some of you, or many of you, I'm sure all of you are going to appreciate. It's going to be free thanks to our sponsors. I think that's very important. I think we would like this community to grow, and we'd like everyone to be able to take advantage of this event. So some highlights there: 5 days event, more than 50 presentations, 4 tutorials. We are going to have 2 panel discussions, one on the venture capitalism and investments into this area, and another one on a very interesting area, tinyML toolchains, which one to use if you want to start doing tinyML. We'll have a research symposium with a kind of deep dive, fundamental, basic research in this area. There will be a late breaking news session for the latest and greatest in this area, because the field is evolving really, really fast. This year we are introducing awards. There will be 3 of them: Best Paper Award, Best Product Award, Best Innovation Award. As I said, the key for this summit is to be interactive, and we'll have quite a few breakout sessions where people can discuss topics of their interest. We are going to have partner session. One area where I'm extremely excited and passionate is tinyML, tinyAI for good, for life, how we can bring all these technologies back to the society. And as I said earlier, the key, we are going to have live coverage starting at the same time at 8 a.m. Pacific time. So you may ask, like, what is there for me, or what should I do about it? Well, first, check out the program, and you will be really impressed. The quality of presentations and the whole program that the program committee put together is really, really impressive. Then register online. It's a very simple process. It takes a couple of minutes, and you'll be there. And then, as I said, we'll have best awards and late news, and by definition, we'd like to do them kind of very late before the summit to make sure we capture the latest and greatest. And the deadline for this is February 28th. So if you or your company are interested in participating in these nominations, please do so before February 28th. And all the details are on the website. You can check details there. Obviously, block out your calendar for that week. It's going to be a lot of excitement, a lot of news at that week. If you're interested in sponsorships, submit your proposal there. I think there are still some sponsorships available there. Talk to your friends about the summit, be an active participant. What is very important for us, share your feedback, because this community is a community of global community of tinyML enthusiasts, experts, professionals globally. So I think we would like to get and absorb your feedback and share this with you back. And if it's going to be a busy week, so If you're going to miss some talks, don't worry. As usual, all videos will be posted on the tinyML YouTube channel, probably like a week after, or shortly, maybe a couple of weeks after this. There will be a lot of material. So I think we are super excited, super bullish about tinyML in general and the summit. So if you look at the numbers, I think the growth is quite phenomenal. So we started the summit in 2019. This is going to be our third summit. And if you look at any kind of dimension, number of attendees, we expect to have over 3,000, probably close to like 5,000 people registered. I think we opened registration a week ago, actually less than a week ago, and in 5 days we are already kind of close to 1,000 people registered for this event. So it's going to be a very interesting global event. So again, hurry up and register, especially if you're interested in tutorials. And then you see the other numbers. So it's really huge growth in all kind of dimensions for the community. So the tinyML tree is growing really fast, thanks to all the excitement, all the interesting work that happens in the community, companies, academia, everywhere, applications. So it's really exciting area to be in. I don't think I need to share this enthusiasm with you. It's obvious. And it's my pleasure also to acknowledge the sponsors. There's quite good list of sponsors. I think as of today, it's 22. And if you're interested in become, or your company is interested in becoming a sponsor, you can send email to sponsorships@tinyml.org. And you see there are multiple levels and multiple benefits there. But in general, sponsors are going to get also very good exposure at the summit as well. Next talk is going to be in 2 weeks, as usual, Tuesday at 8 a.m. It will be given by Dr. Mohammed Zubar from the King Khalid University. And this is going to be also a very interesting topic, more on the application side of things, like how tinyML could be used in dental applications. And if you and your company are interested in presenting your area, your research, please contact talks@tinyml.org. With this, it is my pleasure to introduce Dr. Martino Sorbaro. So Martina is a research scientist at SynSense in Zurich, Switzerland, and at the same time, he is a postdoc researcher at the University of Neuromorphic in the same city. He obtained his master's degree in physics in the University of Pavia, Italy, and PhD in neuroinformatics at the University of Edinburgh in Scotland. And he's going to share his current research on spiking neural networks, both the theoretical basis and the technological applications. So really excited about hearing Martino's story on the spiking. I think that's a really fascinating field. So, and the stage is yours, Martino.
Thank you. Hello, everyone, and welcome to my talk. Thanks for coming. Good morning or good evening, depending on where you are. So my talk today is going to be about visual classification for always-on devices with a very low power consumption. We're talking about below 1 milliwatt, using spiking convolutional networks on our company's chip, which is called Dynap CNN. I understand that the audience backgrounds are quite broad, so this talk is going to be partly academic and researchy and partly about applications, and it's going to have more technical sections and more basic sections, so hopefully everybody can enjoy at least parts of it. So I'm talking about neuromorphic solutions and neuromorphic hardware, so let's start by talking about what neuromorphic means, or at least what neuromorphic means for me, because there are different uses of the word neuromorphic. So let's go through this a little bit. Okay, so if we talk about standard deep learning, not only we are usually talking about an algorithm that's a neural network that learns that runs on a PC and on a GPU or a CPU or a TPU, depending on what you have. It can also run on some specialized hardware, like certain accelerators. And because this is tinyML, many of you will know about these, probably more than I do. But the main difference, I would say, in the kind of neuromorphic engineering that I'm talking about is not only that it runs on specialized hardware, but that we are talking about spiking neural networks. These are networks that resemble more, or slightly more, if you want, what is actually happening in the brain, which is that neurons send discrete signals to each other, which are called spikes in neuroscience, or action potentials. And that the whole network works in an asynchronous way. So each neuron can spike at any time, independently of the others. And the time is continuous. So the network actually resembles more like a physical system that evolves in time according to certain equations, rather than what you have in a standard neural network, which is essentially a function that connects input to output. So with a bit more detail, in standard deep learning, you have an output, which is essentially just a function of an input weighed in a certain way, plus a bias, and then going through a transfer function, for example, a rectified linear unit. So this is what a neuron does. In a neuromorphic model, a spiking neuromorphic model, because as I said, the word neuromorphic sometimes recently has also been used for different kinds of applications. In a spiking neuromorphic model, the neuron has an internal state, which is corresponding to what in neuroscience is the membrane potential of the cell. And this state evolves in time, and that's the main difference. And then usually when this state reaches a certain threshold or certain conditions apply, then the neuron emits a single spike, which is then the output event function that also depends on time. So I hope this is clear. And now we talk about why do we want to do this kind of thing? Why are we doing this? Because building a neuromorphic chip is a relevant solution for on-edge applications because of the very low power that it uses. So first, the network is essentially silent all the time, unless there is a signal that needs to be carried through the network and the computation that needs to happen. And that's one advantage, the sparsity of the whole thing. So because it's specialized hardware, the power consumption can be kept much, much lower compared to a computer, of course. So the possible applications are things that, if you're interested in tinyML, you may already be familiar with, and is essentially anything that requires an always-on artificially intelligent algorithm, something that can continuously monitor a signal and uses very little power so that it can be carried around on battery, for example. So we have use cases like embedded healthcare, where we have a device that stays with the patient. We want to have always-on audio processing, like when you have for example, a keyword spotter. Imagine an Alexa keyword spotter or something like that, except that it runs on battery and it doesn't need to send the signal to a cloud to be elaborated. Same for industrial monitoring. And then, of course, these that I've just told you are examples of low dimensional signals. For audio, you have a few inputs corresponding to different frequencies, for example. And then we tend to talk about vision applications somewhat separately, because the input in that case is very, very high dimensional. You can have thousands of pixels, or even, of course, megapixels, millions of pixels coming in as a signal at any given time. So the problem is quite a bit more challenging. And the applications of these are any kind of visual detection and tracking on autonomous vehicles, small devices like phones, cameras, mobile things like drones. And the vision side is what I want to talk to you today a bit more. In my company, there are also other people that work more on biosignal processing and auditory processing. But the vision side is my field of expertise, and also is the one where we have currently a chip that we would like to present. So let's talk about this chip for a moment. This is the Dynap CNN that you see here in the middle of the picture. That's the chip. And what is interesting about it is that it's a convolutional chip. So it's designed to implement convolutional spiking neural networks. And in particular, it has 9 convolutional layers, each of which has also a pooling layer associated to it. So 9 convolutional layers means it can support a reasonably large network, even if not something that you can do 1,000 class ImageNet classification with higher reliability, of course. But for certain tasks is more than enough. Each of these layers can have up to 1,024 feature channels, depending on the layer. Some are larger, some are smaller. And it has up to 16 output classes. And of course, this is mostly for vision applications, even if anything that a convolutional network can be applied to can be used on this chip.
So Martina, can you talk a little bit about design considerations for this chip? Like why, for example, you decided to use 9 layers, not like 10 layers, not like 11 layers or 4 layers, like some people use for other applications. Yeah, what was sort of like what did you have in mind, the company, when you designed the specific chip? That's one question. And second, in terms of application, is there anything this chip cannot do versus what it can do? What are the capabilities of this chip? Mm-hmm. Or maybe you'll talk a little bit about this later in this presentation.
Yeah. Okay. So the first question was why exactly 9 layers? And of course here, the point is to make some kind of balance. We wanted a trade-off between something that is sufficiently small and sufficiently low power, and something that can do a task. So why the exact number is 9? You should ask my colleague that work on hardware. But we felt that this was enough for the kind of tasks that we wanted to do as a prototype. And indeed it is. So we wanted something to be, at the beginning, to be really quite small, but sufficient to work on some real world task. And as I'll show you later, it does work on real world tasks. So about tasks that it can do or cannot do. In anything that can be done with a small convolutional network can be done with this. And of course, this is because it's event-based, so it's spike-based. It works best with data from the dynamics vision sensors that I will explain in the next couple of slides. But in principle, it can also be used on data from a normal camera. Then we would have to think a bit more how to do that, but it's possible. So a bit more detail about how every neuron in this chip works.
And related to this, I'm sorry, Martina, for interrupting. There is a follow-on question from Sebastian, and he is asking, what is the impact on the power consumption for having more convolutional layers?
The impact on the power consumption if we had more convolutional layers?
Yes.
So as I will explain later, the power consumption depends on the number of synaptic events, so of spikes transmitted from one layer to the next, and the size of the layer. So typically, if you have a bigger network, you will have more neurons, and if you have more neurons, you also have more spikes. And the fan out of every layer is also going to be larger. So then you'll have more power consumption because of that, not intrinsically because of the number of neurons. Okay. But I think maybe this answer was a bit technical, but in a bit I will talk about this a little more. Okay, so a little more detail about, very basic about how this works. Whenever an event is coming from another neuron, this is a signal, which is a spike, that simply signals that the corresponding weight that connects these two neurons should be read from its memory, which is an 8-bit memory within the chip, and these 8 bits of weight value are summed to the state of the neuron. The state of the neuron is the membrane potential, the internal state of the neuron, which is a 6-bit memory. So when this gets to a certain threshold, when it reaches a threshold, it gets reset. And this neuron outputs an event that gets communicated to the other neurons downstream. So that's how it works. And all the neurons can do this asynchronously, independently of each other. There is no global clock on this chip. So
I think there are a couple more questions, comments from the audience, which is great, related to the architecture. What is the question from Gautam? What is the maximum input size to layers?
Every layer has its own maximum input size. For the first layer, currently we normally work with an input size from the camera, so from the vision sensor, of 128 by 128 pixels. So X is 128 and Y is also 128. This can be increased, and we are definitely planning to increase this in the future.
And one more related to this architecture, and that's a tricky one from Shri. How do you introduce non-linearity, for example, like ReLU or other type of activation work for general neural net, which is based on 8, 16, or 32-bit quantization?
Well, correct. Actually, I said 128, but it's not true. It's 256 by 256. I just correction to what I just said. So the nonlinearity is intrinsic in the neuron. So because when it reaches a threshold, that's when it can spike. And when the spike is emitted, the threshold level is subtracted. So if you had a signal that very quickly, because there are a lot of input spikes, very quickly takes it to 10 times the threshold, then the neuron is going to emit 10 spikes. So this is a sort of discrete ReLU kind of response function. Okay.
Please go on. Yeah.
Yeah. So I'm going to now spend a slide to talk about event-driven vision and dynamic vision sensors. Dynamic vision sensors have existed for several years now, since before our company, and but it's I think it's good for people to know how they are and what they do, if for those who are not aware. And so what are they? They are neuromorphic cameras, which also act in a nice asynchronous way. So what happens is that what's the advantage here in the GIF that you see here? That's me. On the left, it's me recorded by a black and white normal camera, and on the right you see a rendition of what the dynamic vision sensor sees. So what you see, first of all, is that if nothing moves, there's no signal sent. And this has the advantage that it means we are not using any power for that because there are no events being sent. And the second advantage is that if we are doing something like action recognition, for example, we can easily ignore, we are already cutting away the background and we are sort of decluttering the image already. We are only looking at things that are moving. And this is also interesting because it's kind of bio-inspired. So that's the retina. That's what the retina does. It's most of the cones and rods in our retina only spike when there's a change in conditions, in lighting conditions, and not continuously. So, and as I'm saying, the signal that is sent is only in this pixel. There's the light, the brightness is going up, or in this pixel, the brightness is going down. So it's getting darker, it's getting lighter. That's the only information that is sent. And what is interesting is that every pixel can do this again in an asynchronous way. So as soon as the light changing is happening, this signal is sent to from the sensor, independently of each other in each pixel. So there are no frames. There is no such a thing as frame rate in this case. But whenever something is happening in the scene with a very low latency, this is communicated. And the final advantage of this kind of sensor is that it has a very high dynamic range. So whether I am in very dark conditions or in the bright spots in the sunlight, this works without need for recalibration or anything. So again, this is not something developed by our company, it's something that existed before. And we have our sister company, Innovation, also here in Zurich, that deals with these things and partners with us on this. But there are also other companies. So how do we use this? The input from the dynamic vision sensor, or DVS, is directly fed into our chip. It doesn't need to go through a computer or anything. And in fact, we are also developing a chip that has on the same dice, on the same chip, both the dynamic vision sensor and the convolutional chip, so that there is no need for two chips, but is a single entity that does both. And that's a sort of intelligent camera. So in any case, whether you're using an external sensor or the same chip, you have the input that is directly fed to the convolutional layers. And convolutional layers, a bit more about them. As I said, there are up to 9, and as in a normal convolutional network, you can change the kernel size, you can change the number of features, you can add pooling, and you can configure the strides. You can also use dense layers if you need, because I mean, in the end, they are equivalent to convolutions. So yeah, in total, you can have hundreds of thousands of parameters and hundreds of thousands of neurons on this chip. And what else? So yeah, so I can also take questions now if you like.
Yeah, I think there were several questions related to this architecture. Let's see.
I know a lot of people are interested in the hardware, but
yeah, there is a question
not
from
my side of the work, so it's going to be a bit hard.
There is a question from France. He is asking, there is no clock. How then are the duration and periods of the spikes timed, since there is no clock in the system? That's a fundamental question.
There's no duration of a spike. A spike is a single instantaneous signal. It's a packet of 1 bit that says something happened. So there is no duration of spikes. And there is also no frequency. Each neuron sends a spike when it reaches its threshold because of events that it has received.
Yeah. There is another clarification question from Jeff. He's asking, can you repeat the description of how information is transferred between different layers? The diagram looks like a single bit, but you also mentioned multiple spikes to indicate magnitude.
Yes, so if there are multiple spikes that indicate magnitude, then these are sent at different times. They are sent one after the other, and they are different spikes. So they are independent of each other. So imagine it's a system that evolves in time. If a neuron is receiving a lot of input, then it spikes in, it fires in rapid succession more than one event. But these are independent of each other. It's not that, the spikes are not different. They don't have a magnitude.
And one more, and then we'll move on. There are many questions coming, which is great. There is a question from Sheriff. The question is, the retina does periodic refreshes, random eye movement. Do you do something similar to refresh history?
So I'm not sure I understand what refresh and random eye movement mean. So here, if the camera is steady and nothing is moving, then there is no input, and this is good. If you really need to see the scene, then you can move the camera. That's also possible. So for example, if I had now, I don't have a camera with me, but if I point it to the office and nothing is moving, then I don't see anything. If I want to see the furniture, which is not moving, of course I can also move the camera. That's so certain applications on mobile objects, like on drone stuff, then that is exactly what you use, is the camera that is moving. And you want, for example, if you want to stabilize the drone, that's what you use.
And there is a related question, and I promise we'll move on after this. There is a question on what if the camera moves?
Yeah.
Does the background start interfering? Does it still save energy? That's kind of a popular question with the DVS cameras. If the background moves, the camera moves.
Well, if the camera moves, then there will be signal sent in. So the power consumption in that case is not going to be zero. The active power consumption, there will always be. But even during the action, even if there are spikes coming in, it's still low power.
Okay.
And yeah, what else can I say about this? Yeah, so we save less energy in that case, but we still save energy. And then of course, whether the camera is moving or is not moving really depends on your application. And whether the background is a problem or not a problem depends on how you trained the network, like in any network.
Sounds good. Thank you, Martina. So we still have many questions coming. Let's maybe save them for the end of the presentation. Why don't you finish to the end, and then we'll go to the Q&A.
I can see that the whole spiking thing can
Yeah.
be confusing if you're not used to it. Yeah, so okay, so how do you train these spiking networks? Maybe this is going to help us understand a little more about them. In a normal artificial neural network, of course, you train this on a GPU normally, and you train it by backpropagation of error through the network. So in this brain-like networks, can we how does the brain train them? And the answer is that we don't know, of course. The brain is especially learning in the brain is very complicated. And neuroscientists know a fair amount about it. And it's currently a very active area of research to understand how networks are trained in the brain. So one possible approach to training this kind of spiking networks is, can we try imitating the brain in doing this? And as I said, this is $1 million problem. I would say more than $1 million actually. There is research being done on this, but I would say it's still on the computational neuroscience side of things. So it's more still a scientific interest rather than a technological interest, how to do training in a biologically viable way. So the way we do it is we ignore completely the problem of trying to be like the brain, and we can use several tricks. Training is not done on the chip; it's still done on the computer because if we wanted to do it on the chip, we would have to imitate the brain really. So we can do it by backpropagation through time. Note that even if the network is not recurrent, so even in a feed-forward network, you still would have to do backpropagation through time, because the network has the membrane potentials, which are they are stateful. They persist in time. So the network has every neuron has a sort of internal memory, which is its own state, and you are forced to do backpropagation through time to take this into account, even if the network is not recurrent. And as you know, if you do deep learning, backprop through time is slow and is very memory demanding. So for some applications, we try to avoid it. And the one trick to do this is to transfer the weight. So we train a normal CNN, an absolutely ordinary convolutional network in the way you train it with PyTorch, as always. And then we take those weights and we transfer them to our spiking network. So the way you would do this is you start from a recording from the dynamic vision sensor here, which looks sort of like this. And then, well, these are, remember, these are not frames. They are actually events, individual and independent from each other. But we make them up, we slice them up into frames. So we accumulate these events into frames. So we turn them into images and we use them to train a CNN in a completely normal way with backprop. And then we take these weights and we put them into a network of the same exact structure, but spiking. This works because it can do what's called rate coding. So where it encodes the information in the average amount of spikes that is emitted by a neuron in a unit of time, so instantaneously. So of course, this has its downsides because we are trying to make a spiking network like a convolutional analog network, which is kind of sometimes defeats the purpose a little bit. So for example, if we train in this way, we lose the advantage of being able to process in time. So we cannot exploit the memory of the network. But for most applications, we find that this makes the whole process a lot easier and faster and works quite well. So let's talk a little bit more about how can we do this. And I'm going to be a little bit more technical here, and I'm going a bit more to the academic side if you want. So imagine a normal analog neural network with its own ReLU activations, for example, rectified linear unit. And then the activation of every neuron is a real number. If it's a ReLU, is a positive real number. So what rate coding means is that this number is converted into the number of spikes that is emitted in a small unit of time. But then I can do this in various ways. I could use this number of spikes, or I could use this number of spikes. And as long as the proportions are the same, for example, here, from here to here, I doubled all the number of spikes. As long as these proportions are the same, then the meaning of the output would be the same. And then we have to find a trade-off, because as I was mentioning earlier, the more spikes we have, the more power we are going to use. But then if we have too few spikes, then we are going to heavily discretize these numbers here. And so we are going to have some kind of discretization errors, and this rate coding is not going to be precise enough. So how do we find this trade-off? So to be precise, as I was saying earlier, what uses power is not the spike itself, but the act of communicating a spike from one neuron to the other. So you have to weigh every spike by how many neurons this spike is sent to. So if this neuron spikes and has 10 downstream neurons is one thing. If it has 100 downstream neurons, I'm going to use 10 times more power. So that's what we call synaptic operations. And so the most intuitive thing to do, if we want to keep this number low because we want to keep the power consumption lower, is to add the synapse number to the loss. That's what any deep learning person would spontaneously do. We put it in the loss, and so we optimize at the same time the performance of the network on the task and the power consumption. But then there's another problem. There's the problem that so here the convolutional network which is the one that we are training, because then we are going to transfer those weights, doesn't know that it's going to be these activations are going to be discretized. And if I push too much the number of synapses, if I push it down too much, then the network is going to have all its activations below the threshold. And I'm not going to see any spikes once I take these weights and put them in the spiking network. So the way we solve that is that we make a convolutional network which is still trainable by backpropagation, but it has an activation function that, instead of being a ReLU, is what we call the quantized ReLU. So it has a stepwise function that tells it that it's going to be that there's going to be this quantization. So it prevents the network from silencing. And the downside of this is that this function here is not differentiable. So when we train it, we have to use a so-called surrogate gradient method, which is essentially means that we pretend when we are doing the backward pass, we pretend that we have a normal ReLU rather than this stepwise ReLU. And this is also something that already exists in the literature, and it works. So I'm going to show you the result of using this method on a couple of benchmarks, and that these are in our paper. It came out in Frontiers in Neuroscience last spring. So that's the result. Here we have the trade-off between accuracy on the test set and the number of synaptic operations that we use for an inference. And we are doing that on the spiking MNIST dataset, which is basically an MNIST of moving digits around the screen recorded with the DVS. That's a benchmark that is used in neuromorphic engineering. So what you see here is that our method is the blue one, is that so the various crosses, the various signs is by different values of the parameter, so by how much we push down the synaptic operations. And you get that for similar performance to the original one, you can take down the number of synaptic operations by about a factor of 10. Whereas with the other method that I compared this to, which is scaling the weights, that really does not allow you to do it as well. So scaling the weight means you take the weights in the first layer, and you scale them up or down, which for the CNN doesn't make any difference because it's scaling variant. But essentially, it's like reducing the magnitude of the input or increasing the magnitude of the input, so it changes the overall activity of the network. All right, so then the accuracy goes down just a little bit, but the number of synaptic operations goes down by quite a lot. And same thing on a Cypher-10 dataset. This is not a spiking dataset, but you can turn an image into spikes by using, I mean, there are various methods of doing that. You can turn it into Poisson spike trains, for example. And so with that, you can say that, for example, for a network around here in the graph, it says that at 90% accuracy on Cypher-10, you get that an inference costs about 1 millijoule. So before we go into more fun things, maybe I can take another couple of questions.
Yeah, there are several questions. I think one is two actually fundamental on training, because you're talking about inference here. Can this chip be capable of doing on-chip training, or it's done externally?
No. Yeah. Training happens on a GPU, on my computer, or on somebody else's computer. On-chip learning is very tricky because on-chip learning has the same problems of learning in the brain, which is that you have to work locally in the network. You don't have a global vision of what the network is doing. If you're doing backpropagation, updating even a single weight requires information of all the weights of the network. And unfortunately, you can't do this in the brain or on a chip, unless you really, I mean, you would have to build a much more sophisticated chip to do something like that. And that's not trivial and is an active research area.
Yeah, we still have many questions, Martino. Why don't you finish the presentation and then we'll try to answer.
If there are questions about training, I can take them now. Anything else I can do at the end.
Yeah, let's do it. Yeah, let's move on.
Okay, so let's go into something more fun. So here's a benchmark. It's called the Ibm Gestures Data Set. So it's a data set from IBM and from also here the Institute of Neuroinformatics. And there are recordings done with the DVS, so it's event-based vision. So it's 10 classes or plus one, which is the other gesture. And these four are examples of how these classes look like. So there's somebody, doing the gestures in front of a camera. These are lab conditions, so it's in idealized conditions and not for a real. It's meant to be a benchmark and not for a real world gesture application. So on this kind of thing, we get about 89% accuracy on a 1 second snippet, but actually it can do it even on a shorter snippet. And we estimate the power used for our network to be 0.33 milliwatt around, so under a milliwatt. For this specific trained network, then you could, depending on, you can have different trade-offs. Yeah, so now a lot of you are going to ask me a lot of questions on how does this compare to this and that. And so I'm going to talk about this briefly, but with the caveat that it is really not easy to do these comparisons. So we can try. This image comes from a paper that I found from Pena and others, benchmarking of CNNs for low-cost, low-power robotics applications. So it uses different kinds of networks. This purple one is a small network that can reasonably be fit on a chip like ours. So let's look at that. And this is run on an Intel Joule chip on a Raspberry Pi and an Intel Movidius, which is a specialized hardware for tinyML, tiny neural networks. And so that's their benchmark that I found on this paper. It shows that, for example, this is about 1.2 watts of power. So per inference, I don't really understand what per inference means because watts is per second. However, we know that the average time per inference is 0.047 seconds. So if you multiply these two and want to get a figure of energy per inference, that would be of the order of maybe 60 milliwatts, something like that. And then yeah, and for Raspberry Pi, it's also going to be like in the order of tens of milliwatts. So but then again, the most important message here is that I think you should take away from this is not what is the exact comparison, but that comparing these is actually a bit difficult because, as I said, in our case, it depends on the input. So if there's a lot of motion, then it will use more power. If there is no motion at all, like in a static situation, then there is no power consumption. Then of course you can adapt this. So if a lot of motion and a lot of input is expected, you can also adapt your network so that it doesn't use all that input. That's also possible. So another problem in why it's difficult to compare these is the different network sizes. If another device supports a much bigger network, then the accuracy is going to be different, the power consumption is going to be different, the input resolution is going to be different, and therefore the kind of task that you can do is going to be different. And then again, the power here that I quoted here is per second, given that level of activity. But then mostly we want to know the power per inference, so per single image. But the thing is that in our pipeline, there are no images. There's a continuous stream of events. So that's the main problem in comparing the two. And this is also true for accuracy. If you ask me what's the accuracy, then usually the accuracy is quoted per image inference. But here we don't have a single image. So I can quote you what's the accuracy in seeing 10 milliseconds of recording or of events, or in seeing 100 milliseconds of events. So I tried another comparison, which is not reported by this paper, which is that, so as I told you in a previous slide, Cypher 10 for 90% accuracy at 1 millijoule, it would take 1 millijoule. And I found on the specs of Ambarella, which is an automotive camera, they claim a power consumption of 3 watts while doing inference at 30 frames per second. So if you multiply those two, it would say that it's 100 millijoules per inference. So that's 100 times more, but then at the same time, their camera can support a much higher resolution. So again, we are comparing apples and oranges. Yeah, any other questions?
Now let's go on, and there are questions, but we'll finish them after the presentation. Yeah.
So then I'm going to show you the fun bit, which is a live demo on how this is like. So So here you see that's the camera, the DVS sensor, and that's connected by USB to the chip itself, which is this thing here. And actually I have one here. So if you see my face, then you will see this. That's our Dynap CNN. I'll show you a better picture later. And the computer is here only as a readout of the signal from the chip and to display. So that's how it works. This is my colleague Sadik, and this is Karsten. He is my boss. I know he's listening. He's the head of another team. So here you see that. Let me stop for a moment. Here you see the DVS input, and here you see the gesture that was inferred by the chip. Here it says waving left hand, waving right hand, fake guitar, arm roll, and again guitar, and again left hand and right hand. I think I sent it back by mistake, so it's the same. That's it. So that's again the benchmark data. So it works if you're standing exactly like the data in front of the camera, because that's how the data set is like. Then if you want a real world application, you need a better data set, as always in deep learning. So, and then another example is this face presence detection. So here we want a device that knows if I'm looking at it. Imagine a phone. If I'm looking at the phone, then it knows. And nothing is happening, or if a hand is in front of the camera, then nothing is detected. As soon as a face steps in, then the output neuron that corresponds to face starts spiking and gives us the signal that there's a face. If there's not, then this is behind, so it doesn't get fooled by seeing somebody from behind, and again the face. We can also try this in a moving camera setting, as my colleague Chan is doing now. So again, the face is there, and that's the rest of the office. And if I'm looking at the office, nothing is recorded. It doesn't say face, and now again it says face. So it's a two-way classification: face, not face. Whereas the previous example was a 10 class classification. So what else is happening in the company? Just very briefly, because we are running out of time. We are also working, my colleagues are working on signal processing in time. If you have lower dimensional signals like audio or biosignals, actually even for vision, you may be interested in something that for which you have time dependencies are important. So we are working on a chip that works like that with recurrent neural networks. And then, of course, we are constantly working on different application scenarios, which we do with our partners, with our customers. So we are always looking for ideas on how to use this technology. So you're very welcome to contact us if you're interested. And then of course, we are also always working on improving our Dynap CNN development kit, which is currently already available, although in limited amounts. But just to say that this chip is there, it exists, and it works. And as I mentioned earlier, I didn't write it here, we're also planning to have a chip with the integrated DVS on the chip. So here it is. That's the Dynap CNN development kit, which is roughly the same that I had here in my office. And we are done. Thank you for coming and for listening.
Well, thank you, Martina, for very interesting presentation on this brain-inspired spiking computing. So we have 21 questions and we have 5 minutes to answer them. So I think we'll have to take some of them to the forum, but let's try to answer as many as possible. So there are 2 questions, one from Samir on the chip size and the technology node. The chip seems to be very big. How big it is, and size and package and die, And also there was a previous question on the technology node that was used to build this chip. And a follow-on question on this was, is it practical for this chip to be below like $1 for like big high volume applications?
So that's already a lot of questions. Remind me
Yes,
what the first one was.
Yeah, the first one was the size of the chip. How big is the chip? Both
Okay,
the package and the chip.
So here you see, so that's the development kit, but actually the chip, the actual chip is about this big.
So what is the size roughly like?
So it's a few millimeters square.
Okay. And what technology node was used to build the chip?
This I don't know, and I don't know if I can say even if I knew.
And one question related to the design of this chip, because typically in the digital asynchronous type of logic, the circuitry is quite complex. So you don't use digital, you use Spike. And how complex is your circuitry to do your chip?
So the chip is digital. It's not that it's not digital, but but the neurons communicate to each other by discrete signals, but it's not an analog chip. There are also analog neuromorphic chips.
Okay, and one more related to the chip design.
Digital and asynchronous.
Yeah, asynchronous. How are the weights stored on the chip?
They're in memory. There is an on-chip memory for each weight and for each membrane potential, which is 8-bit for the weight and 16 for each weight and 16 bits for each membrane potential. Somebody was asking me about the price as well.
Yeah, that was the price.
So I think the forecast or the target price for this is going to be $5, around $5 for the chip that I was talking about that also has the integrated vision sensor. So it's both CNN and vision sensor.
Yeah, great. And there was another question, maybe also related to this, actually two questions. Can your chip work with standard cameras, not DVS type of cameras, or it has to be a DVS camera?
Yeah, you could. Yeah, we could do that. And I think actually some of us are working on this idea. So the way you could do that is to feed the input from the camera directly to the membrane potential, or you could do it by turning the input image into spikes and then feeds those to the network. It's less efficient in the sense that you lose a bit of the potential of the event-based architecture, but it's definitely possible, and we are also working on this. We have already somebody that is interested in this kind of alternative way of doing it.
And two more questions, like broad questions. One is, can you give more details on the neuron models? Is it an integrate and fire type of models, and how do you do those type of models, kind of very broadly?
It's a linear non-leaky integrate and fire.
And those are the only models you can do non-leaky. Can you do? There was another question. Can you do other models than non-leaky on this chip?
So first of all, I want to say for those who don't know what non-leaky means, which is that the membrane potential stays there and doesn't. So because normally in neuron models in neuroscience, the membrane potential resets slowly to 0 by itself. That's leaky. So ours is non-leaky, it stays there. So you can add a sort of leak by adding a bias. You know, the normal bias of these of the neural networks. Those could act as a leak. And then if you want a different neural model, that's possible in principle. You would have, but it would have to be built with a different chip. This chip doesn't support other models.
Okay,
but
thank you. And the last question, actually like two questions. If people want to start playing with the chip and the models, what kind of software tools you have available now, and how much is if you have an SDK, how much does it cost? So like what people can do to get their hands dirty with this type of technology.
So one of the things that we do here and that I do here especially is maintaining the pipeline, the software pipeline. So that's very briefly how the software works. Is you can take a PyTorch model, so a neural network built in PyTorch, and then we wrote software that already takes this model, does its own thing to it, and turns it into a model that is fit for the chip. And this is still a PyTorch model, so you can also simulate it on your computer and make it behave in the same way as it would on the chip. So that's already something you can work with, you can play with, and it's free because the main part of this is open source.
Great. Well, thank you,
so
Martino.
that you can play with. Then if you want the dev kit and play with it on the chip, we are at the very early stages of selling these. And my colleague tells me that the hardware dev kit is going to be $2,000.
Okay.
So contact us if you want to know about this.
I hate to stop here, but we are running out of time, and there are still 20 more questions to answer. They keep coming.
Yeah,
So
I'm sorry about that.
I think, no, that's great. I think we will take them to the forum, and you will be able to answer them on the forum, and we'll post them on the forum as usual. So let's move to the next slide. Yeah, again, it is my pleasure to acknowledge the sponsors. Next slide, please, Martino. So it's ARM, the Software and Hardware Foundation for tinyML. Next is, who's next? Next is DeepLight. They use AI to make other AI faster, smaller, and more powerful. Next, please. Edge Impulse have a great set of tools for AI developer, for tinyML developers. Next. Maxim Integrated. Maxim developed a very interesting chip, Max 7800 for AI inference. Next. Kixo, they have a suite of AutoML tools for embedded AI. And I believe Reality AI is also have a set of software tools for building products. Okay, and the company we've just talked about. Thank you for the great presentation and sharing with us this exciting news in the world of spiking networks. Thank you, Martino, and I believe that's the last one. In 2 weeks, we look forward to see you again, and there will be this presentation by Mohammed Zubair from the King Khalid University at 8 a.m. as usual. And finally, my name is Evgeny Gusev from Qualcomm AI Research, and I was your host today. Thank you for attending, and we will see you in 2 weeks or sooner.